You can see my pointer?
Yeah, looks good. Thank you. Yeah, so I think let me just say a few words. So thanks everyone for connecting to the session. So we have, for the first part of this, of the program, we have 6 talks. And today we have William Schmidke from Brookhaven National Lab from STAR Collaboration talking about JSI production. And you have 18 minutes, and I will remind you when you have 3 minutes left, so there is another 3 minutes for discussion. Yeah.
Oh, okay. Good morning, afternoon, evening, depending on where you are. Thank you to the conveners for organizing this session. I'm going to discuss today JSI production in ultra-peripheral collisions in heavy ion collisions at STAR. I'll begin by reviewing a little bit about ultra-peripheral collisions and the processes that contribute to the E plus E minus channel that we observe. Then a little bit of information about STAR detector and the UPC data and how we select it, what it looks like. And then I have 2 general topics. One is JSI production in gold-gold collisions, and the second one is JSI production in proton-gold collisions, utilizing the unique capabilities of RHIC with polarized protons. Okay, so ultra-peripheral collisions, well, when the nuclei collide at impact parameter larger than their radii, hadronic interactions are suppressed, and there's a large flux of Weizsäcker-Williams coming along with the beam particles. And the photon from one beam particle can undergo photoproduction on the other particle. For example, and shown in this diagram for JSI production, there is sensitivity to the gluon content of the target particle. So yes, I just said the gluon content of gold is probed, and we'll compare to a couple of models that are available for UPC, which incorporate the photon flux from the beam particles, and then the production on gold. Starlight is of industry standard for UPCs. It takes photo production on proton data from HERA and extends it to nuclei with the classical Glauber model. And it accounts for some gluon shadowing, not all, and we will see some results in that. And then there's a model called Sartre, which is a dipole model with BSAT saturation. I should point out there will be a talk later by Tobias Toll, one of the authors on some of these topics. So please see his talk later. And then in P-gold, again, we are probing the gluon content of the proton. And I will show you that there's an asymmetry with polarized protons that gives sensitivity to one of the gluon generalized parton distributions. Okay, so for gold-gold, we'll be observing the JSIs in the E plus E minus channel. So the processes that contribute to this channel, well, first of all, there's this photoproduction of JSI, where a photon emitted by one gold undergoes photoproduction on the other, producing the vector meson. And this can happen in 2 different ways. There's coherent scattering, which occurs off of the entire nucleus. And nucleus being large, it gives us a low PT JSI, or incoherent scattering off of individual, actually, I should say nucleons inside of the nucleus. Nucleons being small gives high PT. And this process can proceed either elastically or inelastically, where the final state nucleon dissociates. There are also a contribution from the 2 photon process, where each beam particle emits a photon, which then produce a pair, E plus E minus pair. Sorry, this is mislabeled, it should be a gold here. And then finally, we have high statistics. We're also sensitive, just like the JSI, we can produce the excited Psi2S state, which can decay either directly to electrons, or there's a feed down channel, which will contribute to our main JSI signal, where the JSI decays, Psi2S decays to something in a JSI, and the JSI decays to electrons. In this sample, we're only sensitive to the coherent version of the Psi2S. Okay, this is the STAR detector. The main components, and most important, is the time projection chamber. It's a slow detector integrating over many bunch crossings, but it provides very beautiful tracking and particle ID through DX. It's surrounded by an electromagnetic calorimeter and time of flight detectors, which are both fast detectors that we use for triggering. There are these forward scintillation counters around the beam. And then not shown in the picture, but about 20 meters from the interaction point are 0-degree calorimeters, which detect neutrons going along the beam path. So the trigger in all of this data requires back-to-back showers in the electromagnetic calorimeter. We veto on these beam counters, which rejects hadronic collisions where the nuclei break up. And then we also require some other signals from fast detectors just to reduce noise and because of high rates. Offline, we reject high activity events in the central detector. We require 2 tracks back-to-back matching the showers in the electromagnetic calorimeter. And then we just select tracks that are well reconstructed. We select electron pairs through DEDX, and we reject hadron pairs. So this is what the data looks like. Shown here on the top right is transverse momentum of the pair versus mass of the pair for electrons. And you see all the high statistics features very clearly. There's a huge mountain right at low PT at the J psi mass, which is the coherent J psi. You can also see a radiative tail going up and to the left. The incoherent J psi stretch up to higher PT, and then stretching along the bottom of the plot at low PT, but across the mass range are the 2 photon continuum. Shown below is the mass distribution for both like sign and opposite sign pairs. There's a small contamination of wrongly identified pairs, contributing especially at low mass. But you see it's very, very clean data. And we take this like sign pairs as a combinatoric background and subtract it for our final distributions. Okay, so I'm going to compare now the processes I discussed earlier to the data. These are actually mass and PT. Now we take the processes I described earlier, generated with Starlight with some modifications. But Starlight doesn't quite match the transverse momentum distributions of the J psi and 2 photon, so they were reweighted to match the data. Also, to the incoherent, which Starlight does not include this nucleon dissociation, that's been added in also. So we pass these processes to the star simulation, and which produces templates which we can fit to the data. So shown here on the left is the mass distribution at low PT, and shown on the right is the PT distribution in the J psi region. So you see, you get a very good description of the data. We see the vector meson peaks, a big lot at the J psi. There's also a small but significant psi 2s peak. The 2 photon distribution is described over the whole range of mass here, over 3 orders of magnitude in cross section. And on the right, we see clearly the 2 components from the J psi, the coherent at low PT and the long high PT tail from incoherent. So we use these templates now to do background subtractions and acceptance corrections. And so first thing we do is we subtract the non-J psi components, the 2 gamma and the feed down from the psi 2s. And we now make a cross section as a function of PT squared, which is approximately T, the 4 momentum transfer. So this is the distribution now in a real cross section. And you see the 2 components clearly. The coherent peak at low PT and the long incoherent tail going out to the highest PT on the plot. So shown on the right are also curves from the 2 models I mentioned earlier, Starlight and Sartre. And shown most prominently here, I'll talk first about the incoherent tail. Well, first of all, Starlight is vastly overestimates this. It has a rather simple model for incoherent production and just not adequate. But you see the Sartre cross-section is very close in magnitude, gives a good description. In fact, you see at the highest PT squared, the data rise a bit faster than this model. This could be due to the inelastic, which is not incorporated, inelastic incoherent, which is not incorporated, or subnucleon fluctuations. And this will actually be part of the subject of Tobias' talk later this afternoon. And I urge you to come back and see what he has to say about this. Okay, now if we also subtract the fit to the incoherent, we can isolate the coherent peak. Okay, so you see here's the description. The total cross sections of the whole coherent peak are given here. And you see that Sartre comes very, very close. Starlight undershoots overshoots by about 25%. And this could be just simply due to the inadequate model of gluon shadowing in starlight. Also, the peak is steeper than in starlight. Sartre, as you see, gives a fairly good description, especially of the whole central peak, the shape and magnitude. Both models get the magnitude higher PT approximately right. You'll also notice these diffractive dips in Sartre. In starlight, these are smeared out actually by the inherent PT from the photon, which was emitted by the other beam particle. Within the current statistics, we really can't distinguish very well between these two possibilities. Okay, one last point I want to make about in gold. When the nuclei can also break up through two mechanisms, through Coulomb excitation, where after the initial UPC reaction, additional soft photons are exchanged, which can break up the beam particles. Or in incoherent scattering, by knocking, you actually interact only with one nucleon. You knock it out and you can break up the whole nucleus, giving a breakup of the nucleus. Now, as I mentioned, we have 0-degree calorimeters, which can tag neutrons on either side of the beam in either beam direction. They triggered on approximately the nucleon beam energy of about 100 GeV. And here I take the PT distribution that I showed earlier for the J-psi and break it into the category where there's at least one neutron on either side or where there are no neutrons at all. And you see a very big, clear difference that the high PT usually produces an incoherent, all the tail is here. When there are no neutrons, most or all of the incoherent tail is eliminated. So as this is a good point, this is relevant for EIC, where tagging of coherent and incoherent, separating them, is going to be a very important part of the physics program. Can be compared to also to models such as Beagle, which was discussed in one of the in the future experiments section yesterday. So we have some data that can provide some insight into those into that very important pursuit at the EIC.
3 minutes left.
Oh, okay. Last topic then, I want to talk a little bit about coming to the P gold. Generalized parton distributions, well, these are correlated quark momentum and helicity distributions in transfer space. It provides access to 3D imaging of the proton, quarks and gluons with their orbital and angular momenta. And there are GPDs for each quark and parton species, quarks and gluons, depending on the conservative flip helicity. And specifically, the ones called E are related to the orbital angular momentum. Now, in production with polarized protons, shown in this diagram here, again, we access gluon content through the J-psi production. And there is a possible azimuthal asymmetry of the beam of the production of the J-psi around the axis perpendicular to the beam. The axis is set by the proton polarization direction. And this asymmetry is calculable within GPDs. And in fact, you see through this, it's actually proportional to EG, which is sensitive to the gluon orbital angular momentum. So we can exploit this unique capability at RHIC with polarized protons and with polarized proton scattering. So again, the processes, I'll go quickly here in the E plus E minus channel. The main one is where the gold emits the nucleus and interacts with the proton. This is of interest for this GPD measurement. And it's dominant because of the high Z of the nucleus, of the gold nucleus. There's a small contribution from the opposite process where the proton emits the photon. And there's a continuum E plus E minus process. We don't have the statistics to perceive the psi 2s. So this is again what the data looks like. As for the templates I described for gold, we do the same process for P gold. And here on the mass distribution, you see clearly there's a good description of the data, the dominant photoproduction on the proton process. And also here in the PT distribution, we see the clear J-psi peak and a radial tail. There is some continuum distribution. And in the PT, you see there's a small contribution from the proton emitting the photon at low PT, like in gold coherent, but the dominant one at higher PT is from the scattering off the proton, which is similar to the gold incoherent, which was scattering off the proton. So we want this asymmetry for the photoproduction on the proton process. So you see there's a dominant, the contributions from the other processes here. We simply cut this region out for our asymmetry measurement, and we only include things above 0.2 GeV. So our signal region is in the mass peak, J-psi mass peak, and at PT above 0.2. And we count events for 4 combinations: proton beam spin up or down, J-psi to the left or to the right relative to the spin axis. There's a purity of about 92% for the signal process. And RHIC in this year had about 60% beam polarization. And the final result is this asymmetry, as we measure, is 0.05 plus or minus 0.2 at a photon center mass energy of about 24 GeV. Well, it's a null result, but it's really a proof of principle of an important measurement. These authors, which were cited earlier, had a curve for a higher PT. They remade them. Jakob Wagner kindly remade it for our kinematic region. And this plot shows our measurement compared with their curve. So, well, you can see what's needed to drive to a possible signal or a positive measurement. We would need to go to lower W, where the asymmetry is larger, and get more statistics, obviously. So, well, what is still possible at RHIC? Well, first of all, we also have data from a few years ago with polarized protons, can do a similar analysis, but this is actually at very high W, so it won't really be sensitive to the model as shown here. But now these analyses have showed so far use the central star detector, which covering in W, the photon-proton energy range, is given by this red curve here. Already stars had for some years an inner TPC tracking and NCAP calorimeter for triggering, which extends the region to this green curve here. But coming soon, and I mean soon, starting end of this year, STAR will be running with a forward upgrade, which will greatly extend the tracking and calorimeter very, very large eta, which will extend us to this whole black curve here, which now goes down to very low W. So at future RHIC runs, starting next year, this winter, we will be able to measure at lower W, where we expect a larger asymmetry, and also higher statistics, simply because the cross-section is bigger down here. So we should be able to get sensitivity to, for example, the model of Landsberg et al. Okay, summarizing now, well, I described our results from UPC and gold. We have large statistics, the J-psi processes, and psi2s are observed. But for J-psi, we see the coherent and incoherent components, also the 2-photon. Sartre is apparently giving a very good description of the data, both to coherent and incoherent, both in magnitude and shape. I showed how incoherent processes can be possibly studied through a neutron tag, or can be tagged with neutrons. And then we have some future run. RHIC has 4 more years of running before it stops for the EIC installation. In these years, there will be totally about 7 times more statistics, and again with the extended kinematic range of our forward upgrade. Also, UPC in the polarized proton, we observed J-psi process that we're interested in. We demonstrated the principle of the asymmetry measurement, have a null result here, but again, the future RHIC runs this year, coming this winter, and then PP, and then P gold in 2024 will give us about 9 times the statistics and extended kinematic range, which will give us sensitivity to, hopefully, to the asymmetry and the gluon GPD. So there's still some promising new data coming from future RHIC runs. So I finished there. Thank you very much.
Thank you. Thank you very much for your very good talk. Now, is this time for some quick comment or question? So there are none. So William, thank you very much. I think we will continue with the program, but
Okay.
I invite everyone to discuss with you offline.
Certainly. Okay. Okay. Thank
So
you.
we can go now to the next talk by Tomas Herman from the ALICE collaboration. Thomas, if you can share your screen.
Can you see it in full screen and also my cursor?
Yeah, that's good.
Perfect.
So Thomas is going to present results from the ALICE collaboration on JSI production in UPCs. So please, Thomas.
Thank you. So as was said, it is my pleasure to present the latest ALICE results on JPSI and UPCs. And I will not go with a long introduction, as already the previous talk was focused on the same topic and it was also discussed in the plenary sessions. But let me just quickly highlight the key topics. So what we are interested in is the proton structure. The plot on the right needs no introduction at this conference. And we are actively searching for the saturation at low Bjork NX. And so far we have only hints. No conclusive evidence was observed yet. And if we look on the structure of proton inside the nucleus, so the nuclear structure, we see that the gluon PDFs exhibit nuclear shadowing effects at low Bjork NX, as can be seen on the plot in the middle. And because the onset of saturation is expected to depend on the atomic mass number, it can very well be that saturation may contribute to the nuclear shadowing. Now, the tool which we are using to explore these phenomena is ultra-peripheral collisions. And as was said, the hadronic interactions are suppressed and we are able to measure photon-induced reactions. But it is worth mentioning here that photon-induced reactions also contribute at the impact parameter B smaller than 2R, as has been demonstrated by ALICE and STAR. Now, the process itself, which is connected or proportional to the gluon PDFs, is the photoproduction cross-section. And LHC doesn't stand only for the Large Hadron Collider, but it is also the Light Hadron Collider and the highest available energies. And there are many photoproduction processes which can be studied in ALICE. For an overview of the raw results, you can have a look at the talk by Valerie. And we are able to explore the gluon PDFs at different Bjork NX values, which you can see is connected to the kinematics of the collision by the formula. And we are also able to look at the transverse plane distribution of the gluons because it's related by a 2D Fourier transform to the T dependence or PT square dependence of the cross section. So now let me similarly briefly talk about the detector itself, which we use to measure the data. So in ALICE, the detectors are located in two main groups. That is the central barrel. Here, going through from the interaction point, we have the inner tracking system, which is a silicon detector used for triggering and tracking. Then we have the time projection chamber, which is a slower detector used for tracking and particle identification. And even further out, we have the time of flight detector, which is used for triggering and particle identification. And all of these central detectors are enclosed in a solenoid magnet. And you can also see a view from the event display where you have where we have the JPSI and candidate. Now the second location is the forward rapidity muon spectrometer, and that starts with an absorber which stops anything but muons with high enough momentum. Then there are 5 stations of the muon tracker, which is used for tracking, as the name suggests, with the third station being enclosed in dipole magnet. And at the end, we have another absorber, a muon ball, which is protecting the muon trigger used for triggering. And once again, here we have the event display as well. And you see that on this slide, also on the previous slide, the event display is very clear. The signature is very clear. And that is also thanks to the vetoes we use to enforce the inclusivity and exclusivity condition. So for that, we are using the ALICE diffractive and the V0 detectors, which are scintillator counters, and we require a veto on their activity, which helps to force the exclusivity. And the V0, together with the 0-degree calorimeter, are also used to determine luminosity. On the bottom of the slide, you also see the pseudo-rapidity coverage of the different detectors. So now let me get to the main part of the talk, and that is the results. So let's start with the coherent JPSI. On the left, you see the invariant mass spectra. You can see that this is a very clear signal. This one specifically is the dimuon decay channel. On the right plot, it is the integrated cross-section in the 3 decay channels we measured, and that's the dimuon, dielectron, and then for the first time for us, the proton-antiproton as well. And the dashed line on the right of the plot is the weighted average. So now if we look on the rapidity dependence of the weighted average of the cross-section, we have the data on the plot on the right, the central rapidity data, which it was described now, and also plotted there are the forward rapidity measurement, which has been measured in the past, and it's compared to several models. So just briefly, I touch on the most key ingredients of the different models. So we have the impulse approximation, which is based on photoproduction data from protons, and it doesn't include nuclear effects except coherence. Then we have starlight, which is similar, but in addition, it has a vector meson dominance model to include multiple scattering. Then we have the APS-09 parametrization of nuclear shadowing data, the leading to its approximation of nuclear shadowing data. Then there is a group of 3 models, which are based on the color dipole approach, which is coupled to the color glass condensate formalism, but they differ in their assumptions on the dipole proton scattering amplitude. Then we have the color dipole model with hotspots on the nucleon structure. And last but not least, we have a color dipole approach, which is coupled with an impact parameter dependent Balitsky-Kovtchenkov equation. So after going through this, we can now have a look at the comparison itself. So let's have a look. By taking the ratio of the impulse approximation and the central measured data, we see that for the Bjorkenx and the order of 10 to the minus 3, the nuclear suppression factor is 0.65 plus minus 0.03. And if we compare with the individual models, we see that the models with shadowing, 2 models with shadowing, and 1 model with saturation describe the central and forward data, but they underestimate the semi-forward data. And the other models, they describe either the central or the forward. So no model describes the data in the full rapidity dependence. A model which would have less shadowing for Bjorkenx in the order of 10 to the minus 2 or 10 to the minus 5, which is the value which corresponds to these semi-forward data, might describe the data better. Now let's move on to the psi prime. So once again, you can see the mass spectra with a very nice peak, but here we have significantly lower statistics. And this, the decay channel which you can see is the dimuon plus pion, but we have 3 other, we have 3 in total, as you can again see on the right plot with the integrated cross-section. The second channel is the dielectron plus pion, and then the last one is dimuon, where the dielectron and dimuon channels are merged together. And once again, the dashed line is the weighted average of the cross-section. So if we have a look at the rapidity dependence, we can do the similar exercise as we did with J-psi and look at the nuclear suppression factor, and turns out to be 0.66 plus minus 0.06. So the result is consistent with the result from J-psi. And comparing to the models, we see that both models which include shadowing agree with the data. And from the models which include saturation, we see that the BBK model agrees. However, the hotspot model overpredicts the data. And the starlight and impulse approximation also overpredict the data. And now this was all for the rapidity dependence measurements. And now let's have a look at the first measurement of the coherent shape psi t-dependent cross-section. So this result was recently accepted by physics letters P. And to get to the t-dependence, we start from a pt square dependence. And we need to make several steps. So to make the transition between the variables, there is an unfolding method which has been done in 2 different ways. There is also a correction on the interference of the photon sources. And to get from the UPC photoproduction cross-section to the photonuclear cross-section, one needs to use the photon fluxes. So after completing these steps, we are able to probe the transverse gluonic structure of the nucleus at low Bjorkenx. So let's now focus on the plot itself. You can see that the difference between the data points with respect to the starlight prediction, which is driven by the nuclear form factor, is in both shape and magnitude, and this demonstrates the t-dependent QCD dynamical effects. We have also 2 other model predictions which describe the data within the current uncertainties, and that is the LTA model with nuclear shadowing, and the BBK model with gluon saturation. And future measurements should allow us to distinguish between the two models. Now let's have a brief look into the future. So recently it has been demonstrated by Jose and colleagues what can be the impact of the ALICE and LHC UPC results. They reweighted the EPPS 16 NPDFs with the LHC results from run 2 by ALICE and LHCb and run 1 by ALICE and CMS. And you can see on the plot on the right the significant decrease in the uncertainties when we go from the blue area to the gray area. Now looking at the future measurements, for LHC runs 3 and 4, we expect a factor of 13 increase in the integrated luminosity. Then ALICE will operate also in a continuous readout mode, and this will yield a higher data collection efficiency. And we have also significant detector upgrades. If you want to hear more details about this, you can have a look at the talk by Marcus. Anyway, the result is we will observe millions of shape size to be recorded by ALICE, and also very impressive numbers for the other vector mesons. So this means we will have improvements in the statistical precision as well as systematic uncertainties and efficiency, which will mean a significant increase in precision on all our previous measurements. But that is not all. We will also be able to make new differential measurements, like the double differential cross-section in rapidity and T, or the angular dependence between the dileptons. And that is not all. We should also make completely new measurements, like observation of the epsilon-1s state, which will allow us to look into a new kinematic region with the Q square being a factor of 10 larger than that of the shape psi. Or we could also explore the interference effects. Now this brings me to the conclusion of the talk. Our results demonstrated that the gluon structure at Bjorken X in order of 10 to the minus 3 demonstrates a nuclear suppression factor around 0.65. We also saw the T-dependent sensitivity to the gluon distribution in the transverse plane, and models with shadowing or saturation describe the data within the current uncertainties. And there is a great potential of the UPC measurements to significantly decrease the NPDF's uncertainties. And if this is not exciting enough, then for the future, we will have major improvements in run 3 and 4. So plenty of new and improved results will come on the way. Thank you for your attention.
Thank you for your talk. So we have, we have time for questions and comments. Paul.
Thanks for the nice talk and very nice data. So you distinguish between nuclear shadowing and gluon saturation, so a sort of an effect that happens in nuclei versus an effect that's due to partons. And I mean, on slide 19, you said you hope to distinguish between these two separate models, LTA for shadowing and BBK for saturation. I mean, are you claiming that you can tell the difference between those two phenomena or just those two models?
The two models.
Okay. And if you, I mean, is there a way to distinguish, do you think? I mean, I'm thinking if you did, I mean, if you can do this off protons and compare it between protons and nuclei or different nuclei, maybe they have different dependencies on A.
Well, yeah, that's a good question. I'm not sure that would be a good theoretical discussion to see if how we can measure an effect which would demonstrate the difference between the two. Yeah.
Okay. But yeah, very nice. Thank you.
Thank you. Are any other comments or questions? Thomas, can you tell us, following up the question by Paul, what are these results are for gamma, for lead-lead collisions, right?
Yes.
Do you have any plans to measure this also, like in protons, and do comparison? Is there?
The analysis on the proton lead data sample is ongoing, and we hope to get some results in the future. Yes.
Okay. So it's this. So if there's no additional comment, so thank you, Thomas. This was a very nice talk. I would suggest if we could start sharing the talk by Agnieszka. Michal, if you want to share your screen.
Yes. Okay, you should see now.
Yes. So Michal Krelina is talking on the momentum transfer dependent on heavy quarkonia electroproduction. Please.
So, hello. First of all, I would like to thank the organizers for this opportunity. And I would like to speak today about the T-dependence of heavy quarkonia electroproductions, and I would like to focus on the importance of the dipole orientation. So, okay. So that is an outline. So it's based on a paper that is at the archive. And so let's start. Some echo. Okay. Okay. So there is some motivation. So as you probably you listen many times, the motivation for heavy quarkonia is, for example, because it's good probe for heavy ion collisions, or for study the saturation phenomena in EP or EA collisions. So especially in the latter case, it's a very natural way to use the color dipole formalism for such calculations. And however, there are many uncertainties. Apart that the dipole orientation, there are many more, like the choice of your quarkonium vertex, or the choice of your wave functions, specifically what QQ bar potential you use. That are uncertainties that are also significant, but you can find, for example, in these other papers, and it's not the subject of this talk. Also, there are other interesting topics in this area, like NLO calculation. You can see or actually replay the talk by Tomas. Okay, so very shortly about the color dipole formalism. If you want to calculate some T-dependent differential cross sections, basically you need some amplitude that is transverse momentum dependent. So here you can see the structure of the amplitude. It looks pretty standard. So it means that you have some wave function of the virtual photon that goes into QQ bar. Then you have some term for an interaction of the QQ bar with your target, in this case the proton, and then that wave function that your QQ bar goes into some quarkonia. And I will focus on this term of the actually what we call usually dipole cross section. In general, as I said, dipole cross sections describe the interaction of QQ bar with a proton. In general, it's not theoretically really calculable, but so we have only model, but we have pretty good ideas what is behind. Most common interpretation is based on Gluon distribution functions. So on the market, there are many models like GBW, KST, IPSAT, BCBK, different options for BK, CGM, CGC, and so on. But most of these models are fit based on DIS data, specifically on Barton distribution function. So it's not proper way, because in that case your dipole cross section is integrated over impact parameter B. That is so you don't have any information that you need for calculation of the T dependence. So there is just again so the basic idea that the dipole cross sections consist of some unintegrated Gluon structure functions. That is basically a function of Bjorken X and some momentum. The most common phenomenological approach is that you use Fourier transform. It means that then a transfer momentum you prefer some impact parameter space. So basically, what you need some amplitude that is function of the dipole orientation, and it's a distance from the target. And of course, it needs to apply if you will integrate this over B. You should get the original total dipole cross section. Okay, so now is question how about the B dependent? For the first view, what is the common in general in physics? The first approximation, you can use some Gaussian distribution. One example is the IPSAT. So here you can see the amplitude has standard exponential form. Here is some D-sharp evolution, and the B dependence is described by Gaussian, usually by some fixed or also some fit slope parameter. However, so you can see that in this case, the rho or R is completely independent with B. But is it like that? Probably one can imagine that there should be some correlation, because let's see picture how looks situation. We have some at the beginning. We have some vector photon that go in QQ bar. The position of QQ bar is described by vector R in general. So it's an absolute value, say how far they are from each other. And the other vector is the B vector impact parameter that describes the distance from the target to the center of mass of the QQ bar system. And specifically this case, when R and B vectors are parallel, is the easiest one, but also it gives you the maximal contribution. But it's easier for calculation because you don't have no angle dependence. But one can imagine, in general, there is some angle between the vector R and B. So in real life or in more precise calculations, you should integrate over all angle theta. But of course, it's much more challenging. And for example, especially if you use BK, where you have apart also some evolution that is even more challenging. So far, my colleagues, they work on this topic. So far, they have when they are B and R are parallel. But as I know, they also work on general case. Okay, so now I will introduce you our approach. In our case, the model for the dipole interaction is based on the Born approximation for two gluon exchange, approximately in this form. Then the form of the unintegrated gluon density has this form that is where you can use parameters for some standard dipole cross sections. So, and of course, if you build such some new model, you need to fulfill some conditions. In this case, that in case that the B and R are perpendicular, they need to give zero contribution, and opposite, if they are parallel, it should give you maximal contribution. So if you will put together, you can derive such a quite nice amplitude where you have some effective slope. And the advantage of this formula is that it's quite universal, and you can use parameters for all dipole cross sections models of this form, of this quite, I would say, standard exponential form, like it's GBW or BGBK, where actually BGBK is basically the same, only it has the D-sharp evolution of the gluon. Okay, now is question of the how to get the B slope. Okay, there is, as I will demonstrate to you later, it's not very good idea to fit them from the T-dependent data of quarkonium production, because it will fix you your slope, but I will show you later. So in our case, in general, you can calculate the formula for the diffractive slope in general is this form. If you do some approximation, like you will take the fraction of momentum carried by every quark and anti-quark is the same, and we do some simplification using the scanning radius. In that case, you will get some prescription, is approximation. In my appendix, also you can find more details about scanning radius as well as the formulas for even more precise calculation, including for different for longitudinal and transversal polarization. But actually, the difference is pretty small, and this approximation works pretty well. So let's go to the results. So this is basically the main result of this work, where the red line corresponds to the calculations that includes the full RB correlation, and the dashed line demonstrates if you use only parallel orientation. So effectively, what's happening is that if you take only parallel version, your slope is bigger. So if you consider or angles, the effective slope is smaller. Therefore, if I will return 2 slides back to this note, that in case you have one model and you are rely on the field of dependent data, and then you improve your model by this RB correlation, then you probably will need to refit the model again to be in agreement with data, because your slope will effectively change. And of course, the effect change with the energy. So at lower energies, the effect is bigger. At higher energy, the effect is smaller. And even a bigger effect we can follow in the ratios of, for example, psi prime 2s over j psi 1s state. In general, including in our previous works, we found that this way of the ratio of higher state over lower state could be very good measurement in the future in general, that can exclude some models of dipole cross sections, of the wave functions, and so on. So just for comparison with other models, so there is comparison of GBW and BGBK with other models. For all, we use the same wave function, of course, with the different wave function, even with different QQ bar potential. You can put like different up and down like shift. But the agreement we found pretty good for different energies, even for electroproduction. It means for a higher Q square. And again, especially for the ratios, especially for J psi, I mean for Charmonia, the ratios is a pretty good tool how we could exclude some models that, okay, this is better way to study more, this is not so good. Okay, so some conclusion. So basically we calculated T-dependent differential cross sections. And what is the new? We integrate the full BR correlation, so it means between impact parameter and the position of the and the orientation of the dipole. We compare with the models without this correlation, or specifically with model, for example, from my colleagues they use the BK because they explicitly set where both these vectors are parallel. Okay, so as I said, the ratio is a good way how to exclude some models, not only of the dipole cross section, but also, for example, the wave functions, specifically the potential. In general, of course, this is going to be generalized for nuclear target, especially if we have now the new data from ALICE for T-dependence. And of course, if you have a model with a BR correlation, that leads to a specific polarization of the produced quarkonia. So at the end, we should be able to observe polar angular symmetry in the diatoms from quarkonium decay. So basically, the last 2 points are in progress. Okay, thank you for your attention. And if you have some questions.
Thank you for your nice talk. We have a couple of questions. Francesco and Anna. Anna, do you want to start first?
Yes, thank you. Thank you very much. This was a very interesting talk. So basically, I guess the expectation that I would have from what I know from the solution of the BK, one observes this correlation, and but it's also that depends on the relative sizes of B and R. So what we saw at some point was kind of a peak for specific values of R and B. And so in terms of your Q square and W dependence, I would expect that you would also see Q square dependence. So the asymmetry should vanish at large Q square. So it should be the highest at lower Q square or for lower Q square. And also it should vanish at large energies, W's, because then the impact parameter, you should have an expansion in B. So do you observe the Q square dependence that would lead to vanishing of this correlation?
Right. I think I don't have. I have only for photo productions, but you are right. For example, especially for the ratio, you should observe going to more constant, especially for a higher T. But
so,
yes,
for example, you could have a calculation where maybe like you know, some lighter vector meson, and then you take a Q square dependence, and then I think as you move the Q square up, you should probably see vanishing of this asymmetry, because okay, I mean, we saw it in a BK with you know, in a simple BK, and there the correlation is largest when I think R was twice the value of impact parameter or something like that. That was of course stemming from conformal invariance. So it's a simple model. So here you should be able to see it in a Q square dependence.
Yeah, I agree with you, but honestly, I didn't do this explicit comparison, let's say for some non-zero Q square.
Yeah.
And yeah.
So there would be Q square and W dependence. So like you see on these upper plots, you also should it should vanish at large W, right? Yeah.
Okay.
Yeah, that's a good tip. Thank you.
Thank you. Now we have a quick comment about Francisco. If you can make a quick comment, a question.
Yes, thanks. Hi, here is Francesco. Thanks, Michal, for this nice talk. I have just a curiosity. As far as I understand, it's an exclusive process, and it is electroproduction. So what about the production mechanism of quarkonia? Did it include some production mechanism about that incorporates the color singlet in this case, or not? Or the quarkonia is just considered as the dipole itself? Thanks. Okay,
our approach, I didn't put many details because it was subject of the previous work, but our wave function is based, because it's heavy quarkonia, so you can go in the rest state of the QQ bar system. So in that case, in that system, you can solve the Schrödinger equation with some particular potential. We have in our work used, like, for example, 5 different QQ bar potential. Then this solution, this wave function, you can boost to the light cone, and especially we add also something that is called Miller spin rotation that represent, because that solution of Schrödinger equation is solution only for orbit radial part, but not usually the spin orbital part is neglected. So that mechanism of Miller spin rotation also give you correction for this spin orbital part directly in the light cone. So this is the way how we describe the wave function of the vector meson.
Thank you so much, Michal, again for your talk and for the discussion. We thank you again. So we go now to the next talk by Izabela Babiarz. So Izabela, if you can share your screen.
Hello. Yes,
Hello.
I'm here. I'm starting the sharing.
Thank you.
Can you see my?
Yes, very well, Izabela. So Izabela is presenting today her results on central exclusive production of eta C and chi C. So please, Isabel.
Hello, everyone. First of all, I would like to thanks to the organizer to have opportunity to talk today. Sorry for my mouse, but I have a little bit trouble. I hope that this light pointer is enough. Today I would like to talk about exclusive production of eta C and KC0 in the new derived approach, light front KT factorization. And this work was done with collaboration with Roman Pasecznik, Wolfgang Schaffer, and Antoni Szczurek. Okay, sorry. This is the very well-known spectroscopic picture about charmonia, and today I will focus on eta C, which is a pseudoscalar meson described by S wave for the CC bound state, and also the scalar meson KC0, which is described by P wave. And this picture originates from particle data group, so probably all you know this picture. First of all, the central exclusive production, which is a diffraction process, is very interesting because of its final state, and this is a characteristic about with intact proton in the final state, and also we observed the meson. In this case, we observed KC0 or eta C. These kind of processes for the first time were described by Durham group with this kind of matrix elements, and this approach was done with usually very well-known NRQCD approach, also by Pasecznik, Szczurek, and Derayev. But we proposed in our work to investigate in our new approach light cone wave with light cone wave functions, but and for inclusive production, we published a paper in RHIC in 2020 for eta C 1s, and also for KCs. We showed results in another paper. This talk is basically based on the paper which is right now in Physical Review D. So as I mentioned before, the group of Pasecznik, Szczurek, and Derayev derived many theoretical results, but in NRQCD approach, and they did the scalar production, axial vector, and also tensor mesons. But in this case, I would like to talk about only the pseudoscalar and scalar production. In the central exclusive production in PP collisions, the most interesting variables are the transverse momentum squared and also the rapidity of the produced meson, and the other ones like PT distributions. In this kind of processes, we have to also consider the off-diagonal gluon, which are depending on the screening gluon, and one of the on the fusion gluon into the vertex, which is going to the vertex. Okay, so our offshell vertices were previously done for inclusive production, but we also can apply it to our central exclusive production. And for the KC0, we need P-wave functions, and we derived these light cone wave functions for the CC bound state in the approach based on the potential models. So we investigate in our previous papers several potential models, and in this case we take one reasonable for us, and as we can see, we can compose our vertex from these kinds of integrals with inside the light cone wave functions. And for eta C, it is maybe a little bit more straightforward, because we have only one integral inside the vertex, and this integral corresponds easily with a so-called form factor gamma gamma to eta C, which can be measured, but we derived by ourselves and also present in a previous work. So we exactly present the new way of calculating offshore vertices, not in the NRQCD approach, but in the light cone, so-called light cone approach. As I mentioned before, to describe our process, we need off-diagonal gluons. In the market right now, we can find several of them. The most famous, the most known is that one done with by Daram group, and also we find our little modification to this approach only by changing one treatment of a variable. Also, you can find also the CD, we call it CDHI of diagonal gluon, which is a gluon described by Kudel et al. Collaboration. And these are based on the usual gluon in the collinear form by the Sudakov form, the square root of Sudakov form factor, and the skewedness factor. But we also investigate a little bit more, maybe not so famous, but PST of diagonal gluons, which extrapolate gluons from dipole approach. So for the first time it was proposed by this group Pasechnik, Szczurek, Terayev, and it looks like that we have this screening gluon transverse momentum, this GBW group, for example, GBW gluon, and the second one, which is the transverse momentum of fusion gluon, and also the GBW. And also we have to take into account also the Sudakov from the square root of Sudakov form factor, and also here the nucleon form factor, which is described by this formula, but probably everyone knows that this has this form. And also to a little bit investigate more. We take into account the Rasayan-Schmidt gluon, which we take in this form. And what more, in the Sudakov form factor, we take RHIC equal to meson mass square plus gluon transverse momenta. To describe well these processes, we need the gluon which depends on the low scale. So we need a gluon with very low Q squared. In this case, we found gluons provided by Dortmund group, and we in our calculations we used this one, which is the straight line, in the middle line. And also we investigate the Shuvaev prescription of the skewedness correction, because of this factor usually is taken as a constant, and for this kind of processes is equal 1.3 or in the range of 1.5. So we investigate that fact. On the plot on the left, you can see the Chi-C distributions, the distributions for Chi-C in rapidity. So, and we applied this gluon GR from 2008. And as we can see, this effective skewedness factor is about a little less 1.4, but at large rapidity and at small rapidity it's not the rule. We also investigate that fact for eta C, because eta C is calculated for the first time. Maybe it is much more interesting. So as we can see, it's not a rule that it should be this constant value, and in our calculation it looks like that we have a little bit enhancement in the central rapidity.
You have 3 minutes.
But, 3 minutes. Okay. So I show.
Sorry, just 3 minutes plus another 3 minutes of discussion. Yeah.
Okay, thank you. The eta C distributions in T1, T2 for 13 TV. So we can see that these distributions in eta C are not so much large, but we can see a little bit deep near the zero for the T1, T2 distributions. And here we can see that CDH BP, our treatment of QT, and it has a little bit different behavior. The Durham model, and also the distributions where the dipole distributions functions were applied. And we can see that it is much more or less similar. Also, we did these distributions for T1 and T2. We can easily see that these distributions are much more steeper, and it's not dependent more or less on the prescription of the gluon. Maybe the most interested plots. Here we can see the distributions in rapidity. I plotted here all of these gluons for the eta C here, and here in the upper line is our previous result for inclusive production of eta C, and it was a little bit for us interesting that this is much much more higher, this line, and this fact is also shown on PT distributions. But for chi-C0, you can see that the difference between inclusive and exclusive difference is not so dramatic. But you have to know that in these results, there is still no absorptive corrections. Okay, so going to absorptive corrections, we parameterize our absorptive corrections via elastic scattering for the proton-proton. To the Borden level diagram, we add this parameterized elastic scattering amplitude. So we applied this function, which are these variables exactly for the 13 TV, which we find in the literature. So the results, as we can see, these here we can see in the line, the blue line is the results with absorptive corrections, and this green line is the line is without absorptive correction. Only there is only Born level approximation. So we can easily see and say that this so-called gap survival probability is depending somehow on kinematics. And in some places there is a dip, and in some places there is enhancement, or there is not so much difference between Born level. So in numbers, I collected the gap survival probability at mid-rapidity. So we can say that for a chi-C0, the gap survival probability is about 20 to 13% difference, and for eta C, there is about 20 to more or less 30%. And the summary, we calculate transition amplitude for gluon fusion to eta C within a light cone with functions of the bound state CC bar in the framework of potential models. We also proposed a way to calculate the soft effects. Maybe I didn't mention that, but we think that maybe it is the soft effects in the production of eta C in the region of small gluons transverse momenta. And we used in that purpose the GBW or Razayan UGDs, which are obtained from the respective color dipole cross section. And in this way, we extrapolate the off-diagonal gluons. In the central exclusive processes, exactly in proton-proton collisions, we are sensitive to the low scale, especially eta C, which is the main uncertainty in our results. Also in our calculations of the absorptive correction, we restrict ourselves to the so-called elastic rescattering corrections. So in this way, we estimate the gap survival probability for chi-C0 about from 13 to 12%, 20%, and for eta C from 20 to 30%. I really thank you for your attention.
Thank you so much, Izabela, for your interesting talk. So there is time if there is a question or comment. Yeah, I see Rainer has a question. Rainer, please.
Yeah, do you hear me? Yeah, Izabela, very nice. I would like to ask you what I did not understand on slide 12. I mean, you calculate
on slide 12.
One slide before.
Oops.
You show some. You have this table. You have.
Yeah, I know, but I have a little problem
in that table.
to back to. Give me a minute. I will stop share and start share.
maybe you can, which of those are your results now? I did not quite understand which of those are your results. My main question is the cross sections that you calculate. How do they compare to what the Durham group has published 2008, 14 years ago?
These are my results. Okay, I'm stop sharing and now I'm sharing, sorry. You mean this table, yeah?
Yes, this table, which you know, they are, I did not, I mean, these must be calculations that have been published. Now, which are your results also in this table? Are they separate?
These results are only the results from our paper, so I did all of them. I don't know if you...
So, okay, so I understand. So these KMR is Koze-Martin Riskin, they give some prescription and you redo their calculations in...
More or less, yes. Because, you know, there is only prescription that you can use, but you can also think about this in different way. Yes, because we applied a new gluons, and also there is another energy, so it is a little bit different.
Okay, but then let me rephrase, then I understand. Now, how,
yeah?
if you calculate with the KMR, how do your results now compare to what they have calculated 14 years ago? They gave, in their paper, they gave cross sections, and actually we looked at possible Chi-C and we did not see. So we believe that their cross section was too optimistic.
Of the Chi-C?
Yes, Chi-C 0. The other question I had, for some very strange reason in that paper, they did not give the production cross section of Chi-C, but they looked at Chi-C going into the particular decay branch J psi gamma. I think for the reason that at the time this was looked at CDF in that particular channel, but did you follow that approach, or what you give here is the production cross section, not multiplied by any branching ratio?
No, I'm not multiplying by any branching ratio, but I don't know if it is a full answer of your question.
I will say, Isabel and Reina, that this is discussed offline, and also I see Anthony has another question. But
I have no question, but I have answer to Rainer.
Okay, so
can be observed only in pi final channel, and this was discussed by myself and Piotr Lebiedowicz in some paper, not in J psi gamma. Chi-C1 and Chi-C2 may be observed in Chi-C1 and Chi-C2.
Okay.
So
in other words, you have multiplied by the branching ratio of going to
no, this
pi.
number, these numbers which are shown here are not multiplied as
so, okay, gentlemen, I will suggest that we continue with the program.
Okay, thank you, Antoni. Thank you.
Thank you.
Thank you, Izabela, for your interest in talking for the discussion. So now this talk that we have is the last one of this group of talks, is by Piotr Lebiedowicz. Piotr will talk about his result on central exclusive diffraction production of the axial-vector. So in PP collisions. So Piotr, if you have just a reminder, you have 18 minutes, and normally we have, I will give you, when you have 3 minutes left, I will tell you, and then you have an extra 3 minutes for questions or discussions if you want to use them.
Okay, thank you. Hello, Daniel, hello everyone. So first of all, I would like to thank organizers and conveners for giving me the opportunity to speak my contribution. So this work is done together with Joseph Wojtek, Otto Nachtmann, Anton Reban, and Antoni Szczurek. And based on this paper, And so this is Vienna, Heidelberg, Krakow collaboration. In this talk, we will be concerned with central exclusive production CP of axial vector 1285 meson, F1, 1285 meson in proton-proton collisions. So this is relevant diagram, relevant mechanism for this process. At high energies, this should be mainly due to double Pomeron exchange. So we treat our reaction in the tensor Pomeron approach, which was introduced by Karl Evers, Malcolm Maniatis, and Otto Nachtmann. And here, this approach has good theoretical basis from non-perturbative QCD considerations using functional integral techniques. And here in the tensor Pomeron model, we describe the soft Pomeron as effective rank 2 symmetric tensor exchange. I should say that tensor character of the Pomeron is also preferred in holographic QCD, and here are some relevant references. There are by now many applications of the tensor Pomeron model to diffractive processes as photoproduction, DIS. The model was also applied to reaction involving polarized protons. Here, for example, we studying in this model the ratio complex R5 variable of single helicity flip to non-flip amplitudes, and we found that the star data are consistent with only the tensor Pomeron model. So we have treated especially CP reactions with different final state. And here are relevant references. So there are some processes, especially single phi and double phi central exclusive production, which is interesting, very interesting in context of search for Oderon. Okay, now let's go to our reaction. Here are relevant kinematic quantities are standard, so I will not go through them. The Born level Pomeron fusion amplitude is written in terms of effective Pomeron propagator. So Pomeron is tensor, and then it has Lorentz indices, 2 Lorentz indices. And in terms of Pomeron proton vertices. So here are this in the ingredients. We use standard Pomeron trajectory. So these ingredients are known from phenomenology of two-body processes. But in practice, so to give the full amplitude, we should also include absorption effects. And this is done in one channel, a conal approach. So the proton-proton scattering absorptive corrections is convoluted, is calculated as convolution of a Born term and elastic scattering. So KT here is transverse momentum carried around the loop. In practice, we work with the amplitudes in the high energy approximation, assuming S-channel helicity conservation in Pomeron proton vertices. So the new ingredients is Pomeron F1 vertex. And for this vertex must be supplemented because Pomerons are off-shell. And this vertex, bar vertex, derived from covalent coupling Lagrangian, must be supplemented by form factor. And we use 2 types of form factor, this form and an alternative exponential form, where the cutoff constant should be adjusted to experimental data. So in our, we follow 2 strategies for constructing coupling Lagrangian. First is phenomenological approach. In this approach, we consider first fictitious process, the fusion of 2 real spin 2 Pomerons. You can call this also tensor glucose of mass m. And then we ask to give an F1 meson with the spin parity and charge conjugation 1++ for F1 resonance. So here is our reaction. M is mass of the fictitious Pomerons, and epsilon1, epsilon2 polarization tensors, and epsilon is polarization vector. So then we work in the rest system of F1. There are the two pomerons collide head-on to give F1 at rest. The spin. So now we can do angular momentum analysis of this reaction. The spin 2 of these real pomerons can be combined to total spin S, which ranges between 0 and 4. And this must be combined with the orbital angular momentum L to give quantum numbers of F1 meson. There are exactly two possibilities, namely to 2 and for 4. And corresponding couplings looks as follows. So here M0 is introduced for dimensional reasons, is 1 GeV. So G prime and G double prime are dimensionless coupling constants. These coupling constants should be fitted to experimental data. Here are the effective pomeron fields, P K lambda and P rho sigma, with two asymmetric derivatives between, corresponding to orbital angular momentum 2. And this is sort of the field strength tensor of F1 meson. And tensorial functions gamma 8, gamma 10 are known. Now, the second approach which we follow coming from holographic QCD, and it uses the Sakai-Sugimoto model. Here are relevant references, and here it looks much more sophisticated, but the coupling is determined by the gravitational Chern-Simons action describing axial gravitational anomalies. And the Chern-Simons Lagrangian looks quite different, but it has also two couplings, kappa prime dimensionless and kappa double prime has dimension. So for our fictitious reaction with real pomerons, there is strict equivalence. So this Chern-Simons Lagrangian is strictly equivalent to the sum of 2 and 4 Lagrangians. Of course, if the coupling satisfies certain linear relations. For the reaction in which we are interested for the central exclusive production, the pomerons have invariant mass squared T1, T2 less than 0 instead of m squared. So in general, T1 is different than T2, and replacing above in this relation 2m squared by T1 plus T2, we expect for small t still approximate equivalence to hold. So this is confirmed by explicit numerical studies. So let's go to the results. We have compared our calculations with experimental results from WA102 experiment. This is the experiment studied PP collisions at center mass energy 29.1 GeV. They could measure the complete final state. So they gave us cross-section and also dependence distribution in T for momentum transfer from one of the proton vertices. And in phi pp, this is azimuthal angle between the transverse moment of outgoing protons. So you can see that with both LS couplings, and for 4 term, we describe the data well. We can see that the T dependence is very sensitive to the form factor, and we get a reasonable description of this data with experimental form, exponential form, lambda equal 0.7 GeV. From fitting the mean value of total cross-section, we find the values of coupling constant, G prime and G double prime. And absorption effects were included on the amplitude level, and this effect is depend strongly on kinematics and suffers strongly cross-sections. So here is comparison of our results with two different kinematic conditions of absolute value of T, T1 minus T2 smaller than 0.2, left panel, and right panel for larger equal than 0.4. We see again that our model nicely described data. It seems, the dashed line, it seems that the LS orbital angular momentum and total spin for 4 is best reproduce the shape, this coupling best reproduce the shape of the angular dependencies. And almost flat distribution flat distribution at larger values can be observed. This this behavior is mostly due to inclusion of absorption effects, which play significant role, a more important role at this kinematical region. And the absorption corrections are suppressed mostly region in back-to-back correlation in this region of contribution kinematics. Okay, now I will discuss the Chern-Simons coupling and compared with comparison to data. In the left panel, we show our fit to the data. There also interference term can be visible. This result is for ratio, for the coupling ratio of pomeron F1 double prime to prime, minus 1 GV to minus 2. So it's possible to give a relation between the LS and CS Chern-Simons forms of the couplings with these numbers obtained from fit to data, and setting small t, we get this coupling constants. If you compare this number obtained from this fit to this value, you see that the agreement is about 5%. So we conclude that this Chern-Simons coupling corresponds practically to pure 4-4 term. So, but prediction in the right panel are predictions for the ratio of coupling constants obtained in the Sakai-Sugimoto model. So in this model and in this ratio, only one parameter this is Kaluza-Klein mass scale. And for the different ranges of this scale, as is motivated below. So you can see that we agree only with the sign of the ratio, but not on the magnitude. So the Sakai-Sugimoto model predicts rather larger values. But you can see that as is known from lattice gauge, from lattice calculations, the tensor global mass has mass about 2.4. And this corresponds to Kaluza-Klein mass, this number, and correspond to this value of ratio. And this value is close to our ratio from fit. So this value corresponds to dotted line in this panel is close to data. So this discrepancy may be partly due to neglecting the contribution from subleading region exchanges in our model, which can be important at such quite small energies. Okay, to give further constraints in model to pomeron F1 couplings, a comparison with high energy data would be very valuable. This subleading exchanges because this subleading region exchanges, pomeron region, pomeron region, should be negligible at LAC, at least for the mid-rapidity region. So here we show our predictions for the LAC Atlas Alpha experiment with cuts on the rapidity of F1 meson, and for 1013 TV, and for cuts on momenta components of leading protons. And here are our results for different contributions for different couplings. You can see clearly that contribution with the dotted red line gives, with this ratio, correspond to this ratio, gives significantly different shape. So the absorption effects are included, is a larger factor, gap survival factor is larger than for smaller energies. And the absorption is very important, is crucial. It decrease the cross-section, the distribution mostly at higher values of phi and at smaller values of PT. PT transverse momentum of meson, and also T. This could be tested in experiments when both protons are measured. Okay, here are cross sections in microburn for different parameters.
Including.
Okay, I go essentially to my conclusions. The cross sections which we found are larger and depend on the kinematics cuts and on the parameters. Because of the possible influence of non-leading exchanges at low energies where the parameters are fixed, these predictions for cross sections at LHC should be viewed rather as upper limit. We estimated that possible reduction due to regions could be by a factor of up 4 related to the LHC predictions. The 4-charge pion decay channel seems well suited to measure F1 meson in CP. However, F1 is rather close in mass to F2, which also decay into 4 pions, but branching fraction for F1 is larger, 11%, than for F2, and cross-section is also larger. In addition, F1 has 9 times smaller width than F2, and it should be visible in invariant mass distribution. F1 is already seen in the preliminary Atlas alpha results. Here is a relevant reference, and the theoretical studies of the reaction 2 to 6, including both resonances and continuum, should be further considered. This is in progress. And here are my conclusions. We have discussed detailed central exclusive production of axial vector meson in tensor-Pomeron approach. There are different forms of Pomeron-Pomeron F1 couplings are possible. Already, Sakai Sugimoto model gives some predictions for these coupling constants. We obtain good description of data, low energy data, assuming that reaction is dominated by Pomeron exchange. And from this, where we fix parameters, we give predictions for LHC. Total cross-section is large, and differential distributions were calculated. In all cases, we have included very important absorptive corrections. Thank you for your attention.
Thank you very much, Piotr, for your interesting talk. I'm sure there is a lot of discussion. I see Rene with a raising hand, but unfortunately, we have to continue with the program. So I will say if, Rene, if you want to discuss with Piotr offline, and thank you again, Piotr, and everybody on this group of talks. Now we'll move to the next session, and Marta.
Thank you very much.
Thank you, Piotr.